Curiously, around the refinery, usually close to where they're required and where there is. So if you go to the lab, you've got a full range of management for everything that they need. But if there's something that you need and you're in a different location, then you need equipment that's probably done to be there. You know, like over here, they're going to have flocculants and different places that the refinery needs. So I couldn't honestly say that there is any one single place other than the lab which would probably be the most logical one. But that's not something that's on your although it's a very basic one, it's a very good basic one. So how many of you are thinking that the alumina business might be? It's all about the project and getting the marks back. So year 4, you 1 year to go, or next year graduates? So what we have is a 5-unit refinery. So, and within that there are some areas where you will have extra pieces to allow you to bypass if something's on maintenance. So in terms of how many digestion tanks, you know, the process I think would be 5 units, but I know that there's greater one of the others may know exactly what it is. I haven't looked at it. And this one will be one swap machine. So when you look at this refinery, physically it takes up a huge amount of space. And part of the reason for that is back in the 1960s and 1969 when they started construction here, in their heads they were thinking start with 2, add another 3 and then add another 6. So they were thinking an 11-unit refinery. But what happened over time was instead of having to build those extra units, technology allowed them to do that expansion without having to physically build extra capacity. So we did do a major technical upgrade in the late 1990s, and that's when all of that extra business with Alinta came into play because we needed the extra steam. But we haven't had to build any units, so we've got this legacy of all of this extra space, which in its own way creates hazards because, you know, the gardens, the trees fall over and becomes a fire hazard over summer, and so you do need to maintain that. But it is much better than Kwinana if you get a chance to go in there. So anything bigger than this bus is an issue. Anything higher than a certain height is an issue. So I think it's 2.4 metres, you can't go anywhere. If you need to go under a pipe rack. If they have to do a maintenance job and they bring in a crane, you can't get around it, and it's very tight for space. You know, there is no luxury of, okay, let's just park the bus over there. That's not going to be a problem. You really have to physically go and check, mark it off with cones and barrier tape so that nobody steals your spot before you get there. And if you go from here down to Wagerup looks very similar to Pinjarra in lots of ways. The differences being Pinjarra does not have a liquor burner, which Wagerup does. So do you understand the significance of the liquor burner? Okay. Yes, no?
No.
No?
No.
Okay. So the liquor burner is to try and remove some of the organic material that builds up in your liquor stream over time. So basically they siphon off a small proportion of the liquor stream, put it through the liquor burner, and then basically acting as a dialysis system. And then once you've stripped the organics out of that, then you can put that back into your main process flow, and it then dilutes and allows you to sort of limp on a little bit from them. The main issues around the liquor burners there and also at Kwinana have been odour. And when you burn those organics at high temperature, if you don't get your modelling right for where your emission plume is going to land, then you have a lot of very cranky neighbours. So here at Pinjarra, one of the things we have, as you would have driven in, you would have seen all of that farming land around the refinery. Well, that belongs to Alcoa. So that allows us to stay very much within our legislation requirements in terms of noise in particular, and that's the biggest one, even though it might seem a bit nonsensical. At our boundary, we're only allowed to produce 38 decibels of noise. So having that boundary extended all the way out to Southwest Highway really helps us to stay within that legislation requirement. So noise and odour and light as well, because although we're sort of well away from town, you can see the refinery. I live out of Dawesville. You're crossing the bridge at Dawesville, you can see the refinery across the estuary as clear as anything. You know, it's right there as a light pollutant on your, well, they probably like me to say it like that, as a light pollutant.
Yay. 1 2 1 2.
Excellent, well done.
If you want to use it now,
Just lay it on the seat very gently. For now. As long as you're happy with that, you can all hear me all right at this point. So, what was talking about? And the other thing, of course, about this location and also Wagerup is the same, that you've got the refinery in the middle of a farmlands buffer zone that we own, is that it then gave us room for the expansion of the residue areas. So a lot of the stuff around residue management is changing very quickly at the moment, but we still have at Pinjarra over 1,000 hectares tied up in residue management and also water storage, because obviously we need to have high quality water source for the powerhouse. So harvesting as much water as we can at this time of the year, putting it into storage so that we've got it in summer, as well as processed water, which of course we can recycle, but you know, you lose a lot through evaporation. So. Oh, sorry, that we have behind the refinery, we've got residue and water storage areas. So we've got water storage for fresh water, so we've got our own freshwater dam, and then we have also what we call cooling rakes. So this is the processed water that is then, so it gets hot when you're using it to wash the mud and sand, so it's pumped out there to cool before we bring it back through to the process again. So that's our cooling rake. And into that you'll also get, when we build the residue lakes and we put the clay and the liners in, above the liners we put in an under drain system, so that as the water is drawn by gravity to the bottom of the lake, we can harvest that, feed it back into the plant. So it gives us some caustic, obviously what's being leached out of the residue over time, and also the water is coming back into the process. And water has been pretty much, until the last decade, an underrated resource for the refinery, and now it's something that they look at really carefully. They'll probably be a bit blasé this year, because I can see that the lake is very full already, but you know, we don't know whether or not that's going to be an ongoing thing. This is the first year in my life with Alcoa that they have actually closed the mine site to everything. All production stopped because the roads were so bad. It's not pretty.
so where's the mining? Is it all here? Is it?
So no mining down here. Have any of you guys been on the mandatory year 11, year 12 tour? Some no, some yes?
Yeah.
Okay. So from here, if we were to follow the conveyor, not that we got there yet, all the way through. It's 35 kilometres by conveyor to the mine site.
Is that up outside of dwelling, isn't it?
Yeah. So if you turned off, well, it's not so much dwelling up these days as North Dandenong.
Oh, just, yes.
Yeah, so if you go up, if you Google North Dandenong Dam, you will see sitting around the dam the mining operations. That's our current mining area for Huntley. So as I said, by conveyor from there down to here, it's 35, 36 kilometres. And obviously that's sort of like the straight line version of how to get here. Obviously you can only mine where your bauxite is. So that's where the bauxite is, up in the hills, geologically completely different to this area down here on the coastal plain. So where we are now, Perth is built on, Mandurah is built on, and our ancient seabed. And when I say ancient, it's still very young because it's only 40 million years old. So if you turn around and go up the escarpment into the hills, you then are in an area which is something like 500 million years old. So geologically the two are completely different. And the bauxite that we are mining is the stuff that was originally laterites and granites, and was over millions of years, when that block of land was somewhere in the tropics, subjected to constant rainfall. So you had on the mid slopes where you had just the right amount of drainage over millions of years, the water and the organic acids from the vegetation breaking down, basically breaking down the granites and laterites and leaching everything which was water or acid soluble out, and leaving behind alumina, sand, iron and clay. So when you look at world bauxites, ours is quite unique. Of course everyone would say that, you know, it's like your favourite child, it's unique, as are all of you. But our bauxite has, when it gets to the refinery, it should be 33% available alumina, 26% sand, 15% iron and a less than 2% reactive clay content. So we are very lucky in a number of things. We're close to Perth. We have a massive deposit of ore. So we've been mining in Western Australia since 1963. Okay, and we still have enough bauxite for your working life. Okay, so tick that box. Yes, that's a good one. Okay, so our lease expires in 2045, so it's a very big deposit of ore. The alumina is not high, but there's not a lot of chemically reactive clay, so it's really easy to refine as compared to Brazil, for example. I remember what I told you.
Yeah, one.
Okay, we've got the second group on the way. Technical stuff that happens, you know, no control. They use the site.
You want me to start the mud up a bit
Be careful, the floor's obviously wet.
Go ahead.
Yeah, come through. Cheers. Oh, so this is the prop roof. We've got filtration on this side. So look after the residue area. And then we've got thickeners washers on the other side. Yeah, so all we you can see here we've got tank level screens, flows. The screen here is all the back screen. Is all the alarms, so anything that's out of specification, shut off, deviation from a flow set point or a level or a high or low or a pump stop. It's all alarmed. Yeah, one of the other questions we had was like you've got basic PID control loops on basically every different control element, so, and then over the top of that we'll have advanced control, multivariable control that will do the optimisations, and that will basically write set points now to the basic PID controllers and direct them what to do. So given as the process recycles all the way around, so each tank set really needs to take into account what the upstream and downstream tanks are doing when you're balancing flows. So just having a basic control on a single tank set isn't all that effective. So again, yeah, we've got information, schematics of the process with the information on there. We've got see the guys using trends and that, when they're troubleshooting, so flows, temperatures, pressures, what's going on. So yeah. Question?
Alright, what were you thinking of your questions? So, as I was saying to the other group, some of the other stuff, so this probably looks, depending on where you've been, it probably looks reasonably fancy and quite technical. But this is how we actually keep track of what's going on. So it's quite low tech. And you probably see red and green, so red unhappy face and a green happy face. So what we, these are the things which we find most important to control. And we actually, years ago, we went into the Toyota factories, and the Toyota production system was all the rage, and we've been using it in our refineries for about 20 years now. So all of these boards tell what the parameter is we're trying to control. On the left-hand side of that, CDS stands for Controlled Document System. So if you ever worked in a place that's got an ISO 9001 quality system that's a similar piece to that, and it tells you how often we monitor it, what the target is, or the target range that we're trying to control to. If we're in specification, it'll be green. If we're not, it'll be red, and then it'll trigger some actions. Or understand what the problem is, and who's doing it, when they're supposed to have it done by, and what action we're taking. And further after that, so this is fairly dynamic board that's been updated all the time. These ones over here allow us to keep a track, so if the same problem keeps coming up all the time, we can then decide, right, well, we're going to go and do some troubleshooting on this now, and we'll launch. There'll be problems to be solved, and then this really fancy looking sheet here, not very fancy at all. We call this an A3 because it's on an A3 sheet of paper. It's broken up into, and again, this is also from the Toyota production system. So you state what the problem is as you understand it, or the business case of what you're trying to solve. This is the current condition, this is the target condition, and this is the action plan. It's not very sophisticated, but refineries are extremely sophisticated things to manage, but processes you use to manage them, you want to be as straightforward and simple as possible. You've got the best chance of executing them.
Yeah, and I've put a lot of work groups into place, the operations, maintenance, electrical, planning, all of them. So everybody has to be able to see a common set of process conditions and understand where the issues are. That's one of the purposes for it. So. In terms of manning, so we've got 14 in this area, so 14 on each shift. Coverage, so we generally have 2 in the washing area, so looking after 20 washers, 2 in the thickener area, looking after the thickeners and lime slaking equipment, and then they're spotted in the there's a pre-scheduling board up on the telly back there, so that's got all the times for the filter changes, which ones are coming on, which ones are coming off, which ones are being closed, which ones are going on caustic wash. So yeah. So, and all that's set by the CA, and then down in the filter building. Yeah, his operators will be, they've got the same display, so they'll be keeping an eye on that, scheduling all their work.
Are all those areas close to here, like the controlling room, or is it all sort of like?
We'll go for a drive around, but yeah, they're not. Washers up there.
We have the ability to
filter buildings.
centralise,
Yes.
but we generally don't. Whereas it's got a central control room, we don't have one of those.
No.
So is that
You
each
can
area
do it,
has
but we generally only do it in disaster management times.
And it's more to do with the history of how the instrumentation is built up. All our instrumentation comes into most of the rooms behind here, so this this building, this keeps going that way, and there's just cabinets and cabinets and cabinets for wiring and cable trays and that all pouring in. And then we don't have that tied back to a central location except through, it's basically a view only interface. We don't have, the full control infrastructure, control of remotely. So some of it's just historical design. If you design a new refinery, you'd probably have all your control rooms together with all the information, wired just to come back to one point. So like Worsley or Martin and Radius, so the newer refineries are set up like that. So, and that way you basically have room for 3 or 4 times the size, and you'll have the same arrangement for clarification. The digestion guys will be sitting on this side, precipitation on the other side, and they can all talk to each other. Given that it's all one refinery, one flow, if someone's got an issue here, they can talk to the guy next to them and say, look, this is coming. Just makes communication a lot easier.
And you might find that interesting on any refinery that's as complicated as what an alumina refinery is. The vast majority of problems we have in refineries are communication issues. Or you can track back to a communication or a lack of communication or a lack of understanding. So one of the, I guess the biggest things, you go to university for 4 years and learn all kinds of interesting and funky things, but probably the biggest challenge you have when you come out in the workplace is how you take that knowledge and how you communicate that into actions for people who may not have had the same education that you've had to be able to go and act. And believe you me, that is probably more challenging than it sounds. You never stop learning how to do that.
I suppose just, we've got 14 on each shift, there's 5 shift panels here, so that's 70 people looking after the operations. Plus then we've got process maintenance crews, we've got mechanical maintenance crews, we've got electrical maintenance crews, we've got planning, so there's all up, there's 120, 150 people working in this area, so and we'll have the same in digestion, precipitation, residue. So you've got to, it's a big job to coordinate all the work in the area, and alumina processing, there's a lot of maintenance required, it's maintenance intensive. Like we've talked about before, it's either scaling or it's wearing out, so nothing was just operates day in, day out without some care and attention. So. Questions?
What do you pump oxide into those butanes? Which butane is that?
That's a bioreactor storage.
I heard that.
Tank, so we process the oxide in 2 ways. Destroy it through a chemical. We can react it with bacteria, basically, that eat it. So then it's the bacterial processing plant.
Which have their advantages and disadvantages.
Yeah.
Bacterial oxidation is obviously a lot neater, a lot cleaner, a lot easier. I'll say easier. Can be easier to operate. From a process point of view, it will convert sodium oxalate into sodium bicarbonate, and sodium bicarbonate is even less useful for us than sodium carbonate, which is also not useful. So to be able to get it back into sodium hydroxide, you actually need twice as much lime to react with sodium bicarbonate as what you need with sodium carbonate. Whereas the oxalate kiln burns it through the sodium carbonate, but it has all kinds of interesting things about how to run it. And we've learnt a lot about corrosion in metal. Typically that isn't a big issue on a refinery because most of what we deal with is a caustic or a basic environment. But when you go into a bioreactor, it's actually quite an acidic environment. And even when we first built it, as we would do for a lot of other parts around the refinery, we use mild steel pipework and it didn't last 6 months. The bacteria will eat ice holes through your pipes, and I think we've replaced just about everything in the entire system with stainless steel. So material selection is always good fun when you're doing design.
So 51 definitely.
I also understand the process because you might think straight up and it's going to have gas and there's energy, it's heating, it's inefficient. But like they said, the operating cost of the kilns. I think it's probably better than bioreactors and that because of the line that we need to convert the carbonate back to something useful. It's cost effective. When you look at the whole life cycle, there's greenhouse gas emissions and that sort of thing. So yes, the bioreactor is good technology. It doesn't have the direct emission from the combustion, but that's calciner lime, cracker coatings and that process and that. So it's all take the whole life cycle into account, I suppose, when you assess these things.
But you can walk into a alumina refinery and see a power station which is making 120 odd megawatts of power, and do the mental calculations in your head about what kind of greenhouse gas emissions you might be making. But if you then follow that alumina through to aluminium, through the use of aluminium, and perhaps it's in the automotive, you use aluminium to make your car, as opposed to steel, the aluminium cars won't weigh half as much. That's burning petrol, diesel, which is a really inefficient way of burning the amount of emissions that's making. It's all relative. It's very easy to look at one piece of isolation and understand the whole end use pattern. That way, alumina refineries, a modern alumina refineries like this, when we had an emission trading scheme, we actually got credits for what we do here because we use our energy way more efficiently than most of the power generators who don't have a heat recovery steam generator and a customer to use that steam.
I know that eventually it'll become through 40
I suppose the benefit that we got there is that we've got a name for low grade oil. Conventional power station, all that low grade is basically rejected.
You want to tell the power station they've got a great big set of cooling towers on the side of it, or you said the old nuclear pants with the great big mushroom shaped cooling towers, and they just be thumping energy up into the air. With an alumina refinery, the advantage you get is you can consume all of that energy.
Pretty much.
All right.
What's that in my head? Sorry. If you get it on here. Alright, cheers.
What? Yeah, a lot bigger, because I was just in the house, it's like we had our own like separation control room there. I really like it because like everything.
Okay, that's so much easier. What we're going to do is we work our way around back up to the stockpile area. As I said, that's our pickup point in terms of process description, and then we'll loop our way back around with supplementary information from the boiling plant. You'll see a lot more people moving around the refinery at this time of the day than is normal, but you'll notice that they are all moving in one direction. They're moving towards the gate. So for those of you who are asking about stockpiles and capacity of stockpiles, you'll be able to see on your left as we come up the hill the 4 stockpile areas, which are the ore that's going to be processed at Pinjarra, and I'll talk about the stuff that's going to Kwinana shortly. So you'll have here on stockpile 1 a stacker, which at the moment is right down the far end. On stockpile area number 2 we have a reclaimer which is currently undergoing maintenance, so that's one set. And then when you get to stockpiles 3 and 4 you have another stacker and another reclaimer. So this is the only part of the refinery which is not continuously operating. So you've got the stackers linked to the mine site, so when the mine site conveyors are working, the stackers are working. The reclaimers are linked to production requirements over at the milling areas, so you might have noticed that a couple of the mills are offline at the moment, so it could be that they're just being opportunistic and jumping in and doing some of the maintenance jobs. Or it could be that it's broken, and that's the reason that the mills are offline. So this carriage here is what they use to shuffle the reclaimers from one stockpile to another. So we're about to move the reclaimer from stockpile 3 to stockpile 4. and then that boom stacker that's working there on stockpile number 4 will simply swivel around and start to rebuild another stockpile on area number 3. Down to the left. Chevron stacking.
Okay, so as I was just saying, the stockpiles here, the method that we use to build them is chevron stacking, and what that means is that the stacker goes backwards and forwards over the top of itself, and it continually lifts as it builds the stockpile higher and higher. And the reason why you do that is so that you get as close as possible to making blended ore, and it's very important for a refinery in the way that it operates that the ore is as blended as it can possibly be. So when you're operating on a stockpile, this will go for about 3 or 4 days, and you want it to be consistent so that you're not continually having to respond to changes in grade in the plant. Now you can do different types of stacking methods. So at our Wagerup refinery we do another method that's called a windrow stacking, and when you do that you build little piles spaced, and then you come back in and you fill the gaps, so it's like stacking pyramids on top of each other. And that is done because the ore down there is a bigger size. So the size that you can see here, the top size is about 75 mil, and as you can see, if you look at the face of one of these stockpiles up here, a lot of the bigger material tends to concentrate on the outside of the pile, and a lot of the finer stuff stays in the middle. We don't really like that, but it's very hard to avoid it.
So all these stockpiles at the moment are short. We haven't got a full length pile from running all the way down to the front, but when we do, there's probably about 4 days worth of ore on a full size, full length stockpile. So
We should use the mic.
If you look to the other side here, you can see the boom stacker, and that stockpile would be virtually at height, I would say, so they're probably about to switch over. There's no ore coming off that at the moment, which would probably mean that an hour ago or an hour and 10 minutes ago up at the mine site they had a glitch, and there's been a problem at the crushers, so there's been no ore on the system. You might notice that the ore here is much finer, so if you're casting your eye between the stockpiles now on our right, which are going to be processed at Pinjarra, and this ore on our left, you'll notice that what's on our left is much finer, and that's because when it's got here to the refinery, it's been bypassed into a rolls crusher and just passed through that to reduce it in size. So Kwinana started operating in '63. It has old style rod mills. We need to crush its ore down further. So Pinjarra and Wagerup have SAG mills, so they're much more efficient than the old rod mills. So this ore is going to go from here by rail down to Kwinana, sorry, up to Kwinana, it's up, isn't it? To be processed. So obviously processing, same. The only difference between us is that Pinjarra only produces smelting grade alumina, and Kwinana produces some boutique aluminas, as they describe it, for the chemistry industry. So basically they tweak their process at different points to get a slightly different product. So the conveyor on our left is feeding up to the train loader. It's a bit early for the train yet, and there's been one through already today, and this will be the second one, and then there'll be another 2 overnight. So 4 trains a day going through to Kwinana. So coming over the hill, so you see the 2 conveyors coming down over the hill. So they are our only link between the mine site and the refinery. So from the crusher at Myara down to here, it's 35 kilometres by conveyor. It takes just over an hour to get the ore from the mine site down to here. So this is the conveyor that the reclaimer will use when it's, obviously every stacker is having a bit of a glitch, so the system is, they're still running, there's just no ore coming through at the moment.
As you mentioned, the capacity of the stockpiles.
So yeah, if anyone was planning to truck bauxite into the refinery, so they're about 20 to 25,000 tonnes a day bauxite, they're going to get somewhere between probably 50 and 60 tonnes a day. Conveyors
One of the reasons that our conveyor is so efficient is that between the mine site and here there's so many downhill sections. It actually uses less electricity when it's full than it does when it's empty. Because when it's full, the weight of the ore pulling through the downhill sections is actually driving the bill. It's very efficient, isn't it? So conveyors are horrendously expensive to build initially, but your day-to-day running costs are much lower. There's one reclaimer's working right down the far end there. So the stackers are linked to mining. When the crushers are working and the conveyors are running, the stackers will be working. The reclaimers are linked to the milling area. So as they need to refill the bins over at the milling area, then the reclaimers are topping the bins up. So that's the only part of the refinery that's not on a continuous process. You can come up here and you can see stuff working sometimes, and then the next 3 times you come up you won't see anything working.
Okay, so the next section we're about to go through is our milling area, and we've got 7 SAG mills here. 3 of them are earlier designs and they have a maximum capacity of about 215 tonnes an hour, and we have 3 slightly bigger mills which can operate up to about 375 tonnes per hour, and then we have a mill which we put in with our expansion that was done in 2005. It's actually a second-hand mill we bought from the United States. It was used in the cement industry, and it's the biggest capacity one we've got. It can operate at around about 570 tonnes an hour. If you're ever thinking about buying second-hand equipment, we've had nothing but problems with this mill ever since we bought it, so I would advise against it.
One of the reasons it was purchased was just based on lead time, so it's about a 2-year lead time at the time that we were upgrading, so there was a small amount of money net to have been saved by having a second-hand mill, but it was mainly about getting it here on time.
So the mills are all lined with steel liners, so no rubber or poly in any of these mills. They are a great discharge mill, so that means at the end of the mill you've got what looks like floor grading, which holds all of the balls inside the mill, and they have holes about 25mm in diameter which allow the ground product to be able to come out. From there we then send it into a pump, and up to up at the top of the mills there we've got about 7 or 8 DSM Screens. DSM stands for Dutch State Mining, and that is otherwise known as a probability screen, or a sieve bend, and what you're doing is passing your bauxite slurry down across that mill. The near size material and the oversize get rejected back into the mill for regrinding, and the stuff that's ground through to product size then goes through to our next stage.
So the next step for us, of course, is still a bauxite preparation stage, and that's here where we've got the desilication tank. So we've got a set of 9 of those, and basically your holding time here is 10 hours. Yep. So we're adding lime to help react out the organics, so that when we progress into the next stage of the refining process, the caustic will react preferentially with the alumina rather than with the organic material. So basically we just need to take it out, make it inert. Answer, sorry.
Basically 2 things you need there. You need temperature and you need holding time. So you want 95 to 100 degrees and then 10 to 12 hours holding time. 95 to 100.
95 to 100 is a predisilication, which is what you said.
because the refinery was built by unit, so I think Raylene said that we started building the refinery in 1969 and we built unit after unit, so by the time we'd finished putting 5 units in, we'd put 6 mills in, but we didn't start off with all 6 of those mills. So when we put the first unit in, we probably would have put in 2 of those of the smallest mills, and then when we put the second unit in, we would have put in the 3rd small mill, and then as we added the next units, we put in 1 big mill for each of those unit expansions, and then when we did the efficiency upgrade, we added the second hand mill. But if you're doing it from scratch, our Wagerup refinery processes about 7,500 tonnes a day of alumina production, so somewhere in the order of 25,000 tonnes of bauxite, and they've got 3 mills to do that job, 2 smaller and 1 large mill. But you know, you've got to understand that SAG milling technology's come a long way in the last 40 years as well. At one stage, those mills that you saw, so what we would call our mill 4, 5 and 6 here, which are the 350 tonne an hour mills, they were the biggest examples of SAG mills that existed at the time they were built. So if you get your hands on an old SME mineral processing handbook, you'll see a record in there that says Alcoa Pinjarra. So, and you know, when you go up to some of the gold industries now, you'll see SAG mills that are 45 feet in diameter and can, you know, process a hell of a lot of ore through them. So would you build them that way? Well, I guess what you have to consider is when you take that off to do maintenance on it, you lose an awful lot of milling capacity. All of these are original, but what you have is the liner has been constantly replaced. Yeah, every now and then we might get greedy and wear through a liner and start wearing out the shell, but then you've got to rebuild the shell up. We try not to do that. Okay, I'll try digestion as well since we're parked up here. So right in front of us is our digestion area. So again, we have 5 units here. The digestion vessels, you know, you probably call them autoclaves. They are the same thing. They are I guess a fairly tall cylindrical tank with a cone bottom on them, and we are feeding them in series, trying to achieve a holding time of somewhere between 15 to 20 minutes. And with the size of the grinding that we achieve with the bauxite, so we're making a sandy slurry if you like, you need about that much time to dissolve the largest of the alumina particles. So the stuff that's really finely ground will dissolve up fairly quickly, but what you do find is as your alumina is going into solution, the rate at which you dissolve the alumina starts to slow down. So as you're getting closer and closer to the supersaturation concentration you're trying to achieve, then the reaction becomes quite slow, and that's why you need the additional holding time. Now leading into those digesters are a set of heaters. You probably can't see them at the moment, but they are vertically mounted shell and tube heat exchangers, and we will normally go through 4 heating stages. So we have 2 heaters that are in parallel, and they come off the lowest grade flash tanks, which we call blow-off tanks. We then go through a secondary heater which comes off a secondary flash tank with a vapour source, a primary heater coming from the primary flash tank, and then we have 2 additional heaters which we usually operate, 1 duty and 1 standby, which are live steam heaters which are taking steam from the power station, and that is designed to heat the liquor up to about 164 degrees Celsius. We then take the bauxite slurry from the desilication tanks. We add a bit of contact steam to that to make sure that it's about 100 degrees, and we combine that with the liquor to go into our digester, and we're trying to achieve a control temperature here of about 147 degrees. We'd love it to be more, but the pressure limits of what we can operate our tanks at were obviously something that was built a long time ago. If we're designing it now, we would design capability to operate probably over 150 degrees. Yes, so in front of us you can see the flash tanks, and they will drop in height. Over on the left there you can see the tanks which are a darker colour. Those are the digestion vessels.
What's the live steam flow rate into going first of all the
tanks here on the left. So they're sort of like the link area, so dropping the pressure so that we can then progress the process to clarification. So the first step in clarification, of course, is your sand removal. Got multiple questions going. So we've just come past sand removal. So obviously we're using the fact that the sand is coarse and heavy. It's fairly quick to settle out, so we're dropping it down. Into the bottom of the cone so that we can then rake the sand out, pass it over a series of washers, and then from there, assuming that everything is working properly, it's piped out to the residue areas. If there's a problem, it's dropped at the bottom of the building here and then moved out by other means. It's trucked out.
So after sand removal, out here to the left, it's difficult to see, but there's 9 thickeners basically, so thickeners will separate the mud and the underflow goes up to the washer area, which we'll go and have a look at. So from the outside, washers and thickeners look very similar, so there's very little to see. The overflow with the thickeners is then goes through the filtration building, and it's also combined with the overflow return from the washers.
The difference being that back there at the thickeners, we're trying to, everything's insulated because we need to keep it hot. Down here, that's not an issue.
Very good.
bioreactor. So this is one of the areas which we use for destroying our sodium oxalate. The pH of the material in here, well, talking about pH, but we drop the concentration in terms of gram per litre of caustic significantly before we feed in there, and then we're adding CO2 and phosphoric acid and nitrates there to help the bacteria destroy. So it's very important that you keep the pH below 10, otherwise the bacteria don't like it very much. If you get that wrong, then you lose your entire biomass and you spend the best part of the next 3 weeks trying to rebuild it again. Also very important that you keep the temperature below 40 degrees Celsius too, otherwise the bacteria will die. So one of the areas which it really is important that you keep the control very, very tight.
Office areas for various contractors, so that they've got room to keep their stuff on site and have lunchrooms and workrooms, amenities facilities for their specific crews. So although, as I said, there's 1,100 Alcoa employees on site, there's probably almost as many contractors at different times. Some of them are very short term, some of them are long term.
So there's around 2,000.
Like the guys in the canteen have been here as long as the canteen's been here, some of them.
Like I was mentioning, like toilets and stuff like that. You have a lot of people then managing their waste. That's what Bioreactor is.
We've got one of the workshops here immediately on our left. So each quadrant of the refinery has a field-based work crew and a field-based workshop, and also coming up on the left-hand side is all our lime storage. So lime comes into the refinery by road, so here you've got your unloading and storage facilities for lime. This is the new secret stuff. Yeah. Your plant won't have one of these. So this area through here on the right hand side, this is the final step in that clarification process. So here we're passing the liquor stream through a series of lime coated, very, very fine filters. So obviously when it comes out of here, absolutely clear liquor stream is our target. Cali filters?
So Pajara's got 47 filters in there. They're being dumped about every 6.5 to 7 hours. So the filters need to be opened up, closed out. They put that together. It's probably 120 cleaning cycles done each day. So each shift will be doing about 60 dumps. Very labour intensive.
So this is the smallest evaporator that we've got, and it has a different purpose, but you can see the heat exchangers vertically here. So this one concentrates the liquor up that we send to our milling area, and we put it in with the expansion, but all the heaters here on the bottom, and then the flash tanks sit above them.
So as we come up through this area here, we've got all our heat exchangers coming up through on the left hand side. On the right hand side we've got an emergency water supply, so enough gravitational pressure to move that anywhere around the refinery. And then you've got behind that the laboratories, the kiln, and then this building just here, which is very deserted at this time of the day. It means the staff have knocked off and there's no one in the canteen.
So we won't be able to get the bus through the heat exchange or evaporation areas, so all you'll be able to see is from the outside here, but basically there's 7 units of evaporation. What you're looking at is the barometric condensers on the back end of evaporation there, so, and then over behind that building we've got a combination of plate heat exchangers and flash heat exchangers. So,
of the number of people on site, but that's one of the car parks, and that's the motorcycle shed or the bike shed.
So I saw quite a few teams had some elaborate designs for their precipitators, but one of the requirements that you had was 24 hours holding time, and with the flow rates that you've got, you need to appreciate the volume that you need to accommodate. So you'll see the precipitation vessels in a minute as we come around past them, but yeah, there's the practicalities of having complex crystallizer designs, just the capital cost, because of the sheer number and size that you need, tends to be prohibitive, so we tend to stay with a very simple design, so just an agitated tank.
So this is our precipitation area. On the left hand side of the bus is where we do our filtering of our seed. So that's important to get the spent liquor away from the seed before you recycle it into the precipitators. Before we built that, our yield was significantly lower because you end up recycling a lot of liquor that you've already precipitated the alumina from. Directly in front of us there are a whole bunch of precipitators there, so we have 15 rows of precipitators, and I think there are 120 precipitators all up. And you can also see some shell and tube exchangers sitting up in the air. That's what we use for interstage cooling. So between the third and the fourth tank we will cool down quite significantly, so that by the time you get to the last tank you're down to about 59-58 degrees. Now that water that was used for cooling is recycled through. There's some substantial cooling towers out the front of the bus here, which we use for doing the cooling. And then we obviously are adding chemicals to those cooling towers in order to Mount Legionella, all of that sort of stuff under control.
120 precipitated. Wow.
So you're trying to integrate your head exchange as much as you can within the plant, but it eventually gets to the point where when you're cooling down to your coldest point, you don't have another stream to exchange that heat with. So eventually you do need to go to cooling water to meet your temperature.
Okay, so this, if you like, this end of the precipitation is the front end, and what we're doing now is driving down what would be a row of precipitators, and then as we get to the end we're coming into what is our classification area. Now this refinery was built before cyclone technology was really well developed, so back then we built what we call primary thickeners. They are all redundant now, but we use the tanks for other purposes, and that'll be the first of the cone-shaped tanks you see as we're coming along here. After that we then have what we call secondary thickeners, which are very deep cone, conical shaped tanks. You'll be able to see them. And then after that we have what are called tray thickeners, which are essentially 4 beds of thickeners stacked on top of each other into one vessel. Now that is the only one of the classification stages where we're adding flocculant, and it is a different flocculant that we add to this part of the plant than what we add to the other part of the plant up in clarification, because here what we're trying to settle is the hydrated alumina, whereas in the other part of the plant we're trying to separate the mud, which is predominantly iron. So down here we're using a flocculant that is, I guess it's a dextran based, so a sugar based flocculant, whereas up in the clarification area we're adding a polyacrylated acrylamide copolymer, and also with some hydroxamate copolymers hanging off the end of it.
Why would you settle alumina? Oh, so this isn't classified. This is after you come from the precipitation. Oh,
So on the right here you'll see the calciners. So they're taking the hydrate product, the coarsest hydrate from precipitation. So you wash it to get the liquor off it, to clean it, and then you'll heat it up to nearly 1,000 degrees of colding to calcine it into alumina. So there's 7 calciners in there, varying tonnages. The most recent installs on the west side here, that's 7. Got electrostatic precipitators on the stacks for emissions control. Dust. This big one here is about 130 tonne now.
So if you work out here, it's much nicer working on this side of the refinery. There's a lift here, there's a lift there, that's it. So if you don't like stairs, good luck.
technology has gone through a number of iterations since we first designed the plant. So they used to be run as a wet lake operation, so we would send the slurry out there and we would just deposit it in a wet lake way with minimal under drainage. We've since developed it to the point where we thicken it up considerably before pouring it as a thick mud down a prepared incline, and that's to do the deliquoring. When you drove in today, you probably would have seen not far up the access road what looks like a new road that's under construction, and that's because we're in the process of putting in a new filtration plant, and that will be a set of plate and frame presses where you'll be basically pushing the liquor out of the mud, and that allows you to operate with a significantly smaller footprint in the residue area. One of the major difficulties you have running a residue area is keeping the dust under control. So particularly being located so close to the scarp here, when you get the massive easterlies that you get during summer, it's not unusual to get winds over 100 kilometres an hour coming down off the scarp, and that can make keeping your dust, and particularly the residue or the caustic particles in the dust, under control. So a lot of the water that we use in a refinery is for dust control, and the new technology which we're installing now allows you to operate a much smaller footprint. So I guess the dust is going to become considerably easier to control, and our water consumption will go down considerably with that new tech being installed.
Falling trees as well is a hazard, right?
So yeah, the other thing which we haven't gone through is the alumina trains. So when we have finished in the calcination, the alumina is conveyed into a couple of storage bins. So we have one bin which is a day bin, and we will load an alumina train. They're about 38 to 42 wagons in length, and about 2,200 to 2,500 tonnes of alumina on a train. Pinjarra makes about 12,500 tonnes of alumina a day, so you can probably work out we're sending down 5 or 6 trains a day. Now those trains go in 2 directions. We send about 3/4 of our production goes to Bunbury. It goes out that port, gets combined with the Wagerup refinery's product. The rest of it goes to the Kwinana refinery, where it is combined with Kwinana's product and sent out of that port. That allows us to be able to use the 3 refineries to get, I guess, the best of everyone's technologies and achieve a pretty consistent blend on the quality of our alumina. So it doesn't really matter which port it's coming out of, all of the customers are getting essentially the same product.
So as you head back out towards the highway, on your left is one residue drying area, heading all the way down to the bend at the bottom of the road here, and then as you head out west again towards the highway, you run along the boundary of another residue drying area, and that's just 2 of the drying areas. So the drying areas run right back to the railway on the south side here, and basically start at the boundary of Precipitation where we just took the bus. So
I was gonna say, you know the map we have, does it have scale? As they have already, it should have a scale.
Okay guys, if you can just fold your vest back into the helmets, we'll grab those off you. Now, there are some loos just here in the amenities building, They're not flash, but they do work. And if you're about to head on the bus for an hour back to town, you might want them.
classifiers you use for your sand washing?
Rake classifiers.
Rake classifiers.
Yeah.
No alternatives, just that one.
Yeah, they're all rakes here.
Rake classifiers.
So at Wager Up we use belt filters,
Yeah.
rake classifiers and cyclones.
Okay.
So we've got all of them.
Okay.
We're in the process down at Wager Up of building a set of cyclones in series, 4 cyclones in series, but I'll probably do that for the next expansion. Things slowed down a bit when China took off, so
Okay.
yeah.
Then, like, cause we're gonna do the plot plan, and we don't like have an idea of say how big the stockpile should be, or like the area, the land area, in terms of how much the size and.
So that stockpile, if you work on a bulk density of probably a tonne per cubic metre.
I'm a simple man. Google Maps, you would find this half the size of this one, the stockpile's going to be half the size of this one. Or Wager Up's comparable size.
But what I would say is you would build 2 stockpiles instead of 4. You want that length. The longer the amount of time you can put on the ground, the better your refinery is going to operate for it. So yeah, I mean Wager Up runs with stockpiles that are 250,000 tonne capacity. And they'll spend a week building it. And then they'll switch over to the other side and reclaim the one they've just built.
Thank you.
No problem.
One more thing. Oh, sorry. We're just gonna ask where the bathroom was around here.
Right down here. Where
looks like enough.
Oh, okay. Thank you. Please wait for me. I'm going back. Okay. Yes, said they use rake to expire, so.
But we didn't see it at all. Yeah, because I'm